Well, guys, I'm excited to dive into the 2023 FRQ number 2. Should be pretty awesome. Looking at this one, we are looking at a particle motion question with a calculator, so we can definitely expect to be looking at some graphs of functions as well as handling distance, speed, velocity, acceleration, displacement, position, all these fantastic things. So I'm really excited about it. This should be a fantastic FRQ to grow in knowledge and understanding of particle motion beyond just, solving this question. So I'm excited about it. Looking at the question, it says Steven swims back and forth along a straight path in a 50-meter long pool for 90 seconds. Steven's velocity is modeled by v of t equals 2.38 e to the negative 0.02 t times sine of pi over 56t, where t is measured in seconds and v is measured in meters per second. In part A, it says find all times t in the interval from 0 to 90 at which Steven changes direction, and give a reason for your answer. Okay, so we got a crazy function for velocity, obviously, right? We couldn't really do anything with that, but we do have a calculator, so we can definitely do something with it. But let's start with part A. We're looking for times when Steven changes direction. And here's a big part of particle motion. This shows up a ton on FRQs. But changes in direction, I'll abbreviate it, occur when velocity changes signs. So when velocity goes from positive to negative or negative to positive, we will have a change in direction. It's like turning around, right? So a fantastic way to analyze this using a velocity function like they gave us is by looking at the graph. And we can look at places where it goes from positive to negative. So I'm going to go to y equals, click on it, and this gives me a place where I can type in my function for velocity. So I'll type it in, 2.38 times e. If you do second ln, you get e raised to the power of negative 0.02, and I'm going to use the variable x instead of t. As long as we use the same variable, everything will work out the same. And now I'm going to I'll multiply that by the sine of pi, which I believe is second exponent, divided by, I guess I'll do pi times x divided by 56. Oh, all sorts of mistakes for me. But this will be the graph of my velocity. If I were to graph it, I would get something like this because my window is not in the right place. We're looking over the time interval 0 to 90, the first 90 seconds of Steven in the pool. So I'm going to go to window. My x minimum's already at 0, but I'm going to make my x maximum 90 so that I get the full graph. And now we can see a lot of it, but there's kind of this one part at the bottom that we're missing. So what I'm going to do is I'm going to go to zoom, and I like going down to zoom fit. When I click zoom fit, it perfectly fits it right in my window, which is super nice. It gives us a fantastic image of this function. So we're looking for places where velocity changes signs. Looks like right there. It goes from positive to negative, and we need to solve for this value, right? So a great way to do all different types of things with this graph is by going second trace, which takes us to calc. And we have all these different things that we can calculate based on the graph. I'm looking for where it crosses the x-axis, so I'm going to go down to 0. And it's going to ask for a left bound and a right bound. So I'm going to go just to the left of this point, click enter, go just to the right, and get a second right bound. So now you can kind of see these arrows. my x-axis, or the place where it crosses the x-axis, has to be between these points, and it's going to get a really great approximation. I click enter to find the point, and it is at 56. So at t equals 56, and we are in seconds. T equals 56 seconds. Steven changes directions in the pool. Our reasoning is because our velocity goes from positive to negative at t equals 56 seconds. So a fantastic question. Changes in direction show up all the time. We need to be able to check out the graph and analyze it. So that is all we got for part A. And we're going to move on to part B. I really am such a big fan of particle motion questions. I feel like if you can wrap your head around particle motion, like there are only so many questions that they can ask you about it. So I feel like you can get yourself almost a guaranteed FRQ. If you just really understand particle motion, they only really have 6 things they can ask you, right? Velocity, speed, acceleration, displacement, position, distance. They can't really ask you anything else. So if you understand those things, I mean, be excited. This is an FRQ that you probably know is coming. But let's take a look at part B. Part B says find Steven's acceleration at t equals 60 seconds. So, we have our velocity function, but I'm looking for acceleration at t equals 60. Now, a fantastic thing that we know is that the derivative with respect to time of velocity is equal to acceleration. A much simpler way of writing this is just v prime of t equals a of t. So we're trying to solve for a of 60. That's the same thing as v prime of 60. And the fantastic thing is we have this graph of v right here. And we know that the derivative of this graph is super easily solvable using our best friend, which is once again second calc. If I go down to dy dx, I can find the derivative at any point on this graph. I'm looking for v prime of 60, so I'm just going to type in 60. Enter, boom, got it. It is negative 0.036, right? Super easy. They want units of measure. Remember, our displacement distance is just going to be, in this case, meters, right? That's how long the pool is, how far he travels, whatever. Our speed or velocity is going to be meters per second, right? It's a rate of change. And then if we want acceleration, it's the rate of change of velocity or meters per second squared. So that would be our units on this acceleration. Now, that's the first half of the question, but the second half asks us, is Steven speeding up or slowing down at t equals 60? Now, one thing that we know about speeding up versus slowing down, we speed up. I'll write this down. We speed up, and acceleration and velocity are the same direction. And vice versa, we slow down when they're in the opposite direction. So I have my acceleration right here. My velocity, super easily solvable because I have the velocity function. So if I just plug in the times 60, I can see, are they both negative? Are they both positive? Are they opposite? Like, let's figure it out. And the way we do that, once again, back to our best friend, second calc. I go value, and I'll type in x equals 60, and this is going to give us the value of velocity at t equals 60. And it tells me that my velocity at 60 is equal to negative 0.159, and there's a 5, and that'll be meters per second, right? My acceleration at 60, we know is negative 0.036 meters per second squared. So now we're in a fantastic spot, and we look at both of these, and we see that they are both negative. So because both of these are negative, Stephen is speeding up because velocity and acceleration have the same sign. So that is all we got for this one for part B. Relatively easy if you know what you're looking for. All the tools you need are in the calculator for this one. The question is, do you know what you're looking for? Do you understand what the AP is asking for? But now, let's move on to part C. And part C gives us another one of the questions, one of the very limited number of questions that the AP can ask us about particle motion. And it says, find the distance between Stephen's position at time t equals 20 seconds and his position at time t equals 80 seconds. So for this one, we're trying to find the distance between whatever point he's at when t equals 20, whatever point we're at when t is equal to 80. Another great way to describe the difference between a starting point and an end point is displacement. Displacement is literally represented by our final position minus our initial position. So let's think about it. We have a velocity function, right? And we know that the derivative of position is velocity. So if I were to integrate velocity from 20 to 80, this would give me, using the first fundamental theorem of calculus, my position at 80, sorry, I ran out of room, minus my position at 20, which is what we're looking for. That's the displacement. So all I need to solve for is this definite integral. And that's something we just can also have memorized, that the integral from A to B of velocity, that represents displacement. Now, once again, we can go back to our second calc and go down to this integration button. And it gives me a lower limit and then upper limit. For my lower limit, I'm going to say x equals 20. And for my upper limit, I'm going to use x equals 80. Type it in and shades it up. That's one of the most satisfying things about this calculator. And I get that the displacement is 23.38. And because this is a distance, the units are going to be in meters. And this will be my displacement. Now, this is a great way to do an integral when you already have the function loaded in your calculator. If you wanted a different way to do an integral, you could go, I'll kind of demonstrate it, but you can go to math, go all the way down to number 9, and you can actually plug in a definite integral. I could go from 20 to 80, type in my velocity function and solve, and it would get me the same value. So that is all we got for part C. Okay, not too bad. Once again, if you understand that displacement is related to velocity in a ton of ways, right? And understanding how to use that integral to solve for it is integral to solving these types of questions. But now looking at part D, it says find the total distance Stephen swims over the time interval from 0 to 60. Now, here is an important thing about particle motion. I talked about the 6 things you kind of need to know. One of those things is that distance is equal to the integral from A to B of the absolute value of velocity. Now, we talked about displacement being just the plain old integral of velocity. Distance is the integral of the absolute value of velocity. And it asks for the total distance from 0 to 90. So what I'm going to try and solve for is the integral from 0 to 90 of v of t dt. Which for us is great because we can do definite integrals on the calculator so easily. We've actually kind of got it right in front of us. I'm so sorry. Forgot the absolute value bars. That's on me. But I'll just type it right into the calculator right here. Go from 0 to 90. Now, you may be wondering where the absolute value bars, and they're in a little bit of a weird place. If I click on that math button that I used to actually get to this integral, and I go 1 over to the right, I get ABS, which stands for absolute values, or ABS, which I don't have. But we get the absolute value bars when we click enter, and we can just type in the function inside of that. So I'll type it in, 2.38 second ln to get me e to the negative 0.02. And now we are multiplying that by the sine of, it was pi, which is second exponent, pi x divided by 56. And this is my integral. And there are those absolute value bars. On the other side, dx. Let's see, how's the calculator do? The calculator is really bad at solving absolute values. It takes it a while. I don't know why, but it makes my calculator buffer whenever I try and do it. But there we go. We got an answer. So the correct answer to this one would be 138.48726. And that would be our final answer to this question. Now, I'm looking at their answer. It is not the answer that I got. So I'm wondering if I plug this in incorrectly, I might have messed it up. So I'm going to do it again. Maybe I typed something in wrong. Let's try it. So we know going back, it's the definite integral from 0 to 90. And I know it's the absolute value of velocity. So I'll do math, go over absolute value. Perfect. 2.38 times e to the negative 0.02. Okay. Oh, 0.02t, 0.02x. That's what I missed. So don't listen to me too often. You might miss a lot of questions on the AP exam. That would have been mine. But same as before, I type it in, get dx. Now I click enter. Hopefully we get the answer that they have now. It'd be really awkward if I messed it up twice. Let's see. Calculator, come on. There we go. And that is the answer that they have. It is 62.16. And our units are meters because it is total distance, right? So I guess moral of the story for part D, the calculators are not hard to use if you're not an idiot like me. So hopefully all you guys type in your functions wrong, or type them in right, I'm sorry, on the AP exam. And yeah, this one, just an understanding of what distance is in terms of like an integral of velocity or the absolute value of velocity. And yeah, going from there. But I hope that all of this was helpful for question number 2. And yeah, I really hope you guys just do a fantastic job on the rest of these FRQs if you're still working on them. Because these topics, particle motion shows up over and over and over. So it's really important to have your head wrapped around it. But I love doing this with you guys, and I hope that you have a fantastic time practicing some math more in the future. So until next time, I'll see you guys.